Right, hi again. So we need to look at the loop of Henle and the collecting duct in the kidney and how they work. We've already looked at ultrafiltration and selective reabsorption. So the loop of Henle is mostly involved in the reabsorption of water. So it's all about water. So if we draw a kidney, we've got, that's kind of coming in is the proximal convoluted tubule. You've then got this descending limb, it's descending because it's going down, limb of the loop of Henle, and then we've got the ascending limb, it's going up, of the loop of Henle. That then goes into the distal convoluted tubule, which is a bit longer than this, but hey, and then a collecting duct, okay? So all of this here is the loop of Henle. Okay, so key things that you need to know about the loop of Henle in terms of where in the kidney is this happening. If we kind of did an invisible line across there, up here would be the cortex, and then down here would be the medulla. Okay, so just to give you a vague sort of idea of where this part of the nephron is located. Important things about the loop of Henle are that the ascending limb, so the limb that's going up, has very thick walls which are impermeable to water. So the ascending limb does not allow any water through, and that's really, really important to remember. So what's happening? It's quite often easier to explain it in terms of starting backwards, really, with the ascending limb. If I do ions, and just for argument's sake, we're only going to talk about sodium ions, just because it's easier, but actually it's chloride ions as well, and some other ions. But what happens is, in the ascending limb, bearing in mind everything's coming in this way, going out that way, in the ascending limb, ions are moved out into the medulla here. And really important point is that that is an active process. So just making sure we've got a bit of a key going on. Little a in a circle means active transport. So sodium ions actively transported out of the ascending limb of the loop of Henle into the medulla, okay, which is obviously going to make it pretty salty in there, okay. The water, if you think about what's going on here, water coming down, it was actually a relatively high water potential in the descending limb, because not much water's left, so we've got lots of water here. We've got salt out here, so we've got a high water potential there, relatively lower, and please remember we have to talk relatively here because it's not low and it's not high, it's higher, lower, so a lower water potential here, and so water just merrily moves by osmosis out of the descending limb of the loop of Henle. That's great. And what that actually does is mean that if you think about it in terms of water potential, ultimately by the time we get to the bottom, there is a lower water potential than there was up here. And also there's going to be a higher solute concentration because lots of water is left. So we're left with lots and lots and lots of salt, okay? By the time we get down to the bottom here, we've actually got tons and tons and tons of salt. So you will end up with some of it just moving out, just simply by diffusion. So sodium ions will just move out by diffusion because they've built up in concentration because the water has left, okay? Which means that down here, you've actually got a pretty high sodium ion concentration as well. And what you will notice is that you have got here relatively lower, oops, that's a plus, sodium ion concentration, and here it is higher. Okay, so actually in terms of saltiness, it is super salty down the bottom, salty at the top, super salty down the bottom. That's really, really important, because as we come back round here, so water's left, okay, water can't leave here, so by the time we get over to the collecting duct, which we should label really, by the time we get to the collecting duct, we've still got water, and we've got a salt concentration here, and water will just leave by osmosis. Okay, so the more water that leaves, the less water you've got left, so the harder it's going to be for it to leave. But conveniently, we've got even more salt here, so water will still leave by osmosis. So this is an example of a countercurrent multiplier. It's an example of a countercurrent multiplier because we've got a relatively high water potential, and here it is lower, so water will leave. But as our water potential gets lower and lower and lower, it gets even lower and even lower down there, so water will still move out. And this is due to sodium ions moving out. Okay, you do also find that some sodium ions will move in when you end up with a higher concentration in the medulla than you do inside the loop of Henle. Some will move in. So the salt kind of goes around in a big old circle, the sodium ions do. But ultimately, active transport of sodium ions out of the ascending limb makes it a lower water potential here than inside, so water leaves. Water leaving means the water potential will lower and you'll get more more salts, so those sodium ions will leave by diffusion. Water then cannot leave in the ascending limb because the membrane is impermeable to water, which means then that you've got water here. And when we get to the collecting duct, the fact that we've set up this gradient with salty and super salty, water will then leave into the medulla. Just have to remember that there's obviously blood vessels surrounding this whole thing. So if I were to, I'm just going to draw one here because there's like shed loads of them. So that is a capillary. So there's a capillary. Water that's moved out into the medulla will then be reabsorbed back into the blood. Okay, so the point is that you're trying to get the water from the nephron and into the blood, which is where you need it. Okay, the way that this is controlled involves a hormone called ADH, and I'm going to do a different video on that because that's a little bit complicated. Okay, thank you very much.